this area to determine the amount of reinforcement that we need for our maximum moment as we calculated for. We are going to have it as being equals to 7.36 multiplied by 10 to the power 6 divided by 0.95 Fy, and our Fy value is the grade of reinforcement that we are making use of. And within our design data, we said we are going to make use of our mild steel bars, and that one has a grade of 250 newtons per millimeter squared multiplied by 0.95 multiplied by our depth, which is 119. Now punching our calculator through, it gives us a value of 274.12 millimeters squared. So then that is the amount of reinforcement that I require at my tension zone to be able to resist all my tensile stresses. Now, having arrived at the amount of reinforcement required, I need to determine how much of the bars are required. When we're setting out the parameters for our design, we said we're going to make use of mild steel bars of 12 mm diameter. And per our design, we said we are designing for a meter span, or whenever you do a slab design, you normally design for a meter span. So then within that 1 meter span, or from the calculations that we've just gone through, within that 1 meter span, I need an area of 247.12 mm squared of reinforcement. That is the total number of, or the total area of reinforcement I would need within that 1 meter span of my slab, within the tension zone. So then how many 12 mm reinforcement would give me a total cross-sectional area of 274.12, and how would they be evenly distributed within the 1 meter span that we have? How would they be evenly distributed within the 1 meter span that we have? One way of determining it is by finding the area of 1 12 mm diameter bar. One way to determine it is to find the area of 1 12 mm diameter bar, and once you get that area, you come and pick the total area of reinforcement required, and you divide it by the area of 12 mm bar. That will give you the number of reinforcement, or the number of 12 mm bars that you would require within that 1 meter stretch. So then you find the area of 1 12 mm bar, and you come and divide the whole of this value, by the area of the 1 12 mm bar, and that would indicate the number of bars that would be required within the 1 meter span. Now, once you've identified the number of bars that will be required within the 1 meter span, you come and divide the span, which is the 1 meter, by the number of bars. So assumedly, I came out with an area, and when I divided it with the 274.1, it gave me 6 number 12 mm bars. It gave me 6 number 12 mm diameter bars. Now, how would I distribute the 6 number 12 mm bars within a 1 meter space? So then I pick the 6 number, or I pick the 1 meter, and I come and divide it by 6. Whatever I get would be the spacing that should be provided for the reinforcement per the number of bars I have, and per the span over which it is being distributed. Now, another way out is also to go by the steel chart, which has the areas of reinforcement bars and their distribution within a 1 meter span or 1 meter span. There is a steel chart that gives you the number or the area of reinforcement and how they should be distributed within a meter span. The steel chart has been put on the web for you, or it's been put in your V class. So if you go through the V class, you would find the steel chart there. Now, if you go through the steel chart, you'd realize that the area of reinforcement, or if you go through the steel chart and you go through the slab section of the steel chart, you'd realize that the area of reinforcement that is very, very close to the area of reinforcement that we calculated here has a value of 377. The area of reinforcement that is closest to the area of steel that we require has an area value of 377. And that is when we are, or if we are supposed to space our reinforcement at a distance of 300 center to center. So then the closest area to this one has a value of 377. And if I'm providing that amount of steel reinforcement, then it means that the likely distribution of my bars within the 1 meter space will come at a spacing of 300 millimeters center to center. So then, even though I've calculated for an area of 2741.12, I am not actually going to provide the 274.12 amount of reinforcement in my section. But then this is the amount of reinforcement that would be provided in the section. Now, the thing is, once you are using the steel chart, you make sure that after calculating for the area of reinforcement, you find an area of reinforcement in the steel chart which is closer to the area that you've calculated for. So then the area that we've calculated for now becomes our area of reinforcement required. This becomes our area of reinforcement required. So then you pick an area which is very close to the ones that we've calculated for, but then higher than whatever we've calculated for. Because if you pick one which is lower, it means that you are defeating the whole process of the design that you went through. Why do you design and come out with a minimum required reinforcement and choose something lower than that one? So then you choose something which is close to the minimum required, but a bit higher than the minimum required. And whichever area that you choose becomes the area of reinforcement. That becomes the area of reinforcement that you are providing. So then for the calculation we went through, we said our area of reinforcement was given by M over 0.95 FYZ. But then our Z should be less than or equal to 0.95 D, in which place we made use of the 0.95 D as our Z value. So we had area to be equal to 7.36 multiplied by 10 to the power 6 divided by 0.95. Our Fy was 250 and our Z value was 0.95 multiplied by 119, which gave us the value of 274.12 millimeter squared. So then we have this as our area of reinforcement required. Then based on the steel chart, we came out with an area of reinforcement that we are finally providing for the section. And that one has a total area of 300 millimeter squared. And that will provide us, or that gives us the way to space our reinforcement at 300 millimeters center to center. So then we finished designing our section for movement. And so we know the amount of reinforcement that ultimately will be provided in our concrete section. And that has an area value of not 300, but an area value of 377 millimeters, being spaced at a centers of 300 mm. So then based on our maximum moments that we had, this is the area of reinforcement that corresponds to that maximum moment. We had an area of 271.12, and in place of that one we are providing an area of 377, and that will give us a spacing of 300 millimeters center to center. So then you go through the same process and determine the area of reinforcement for every single moment that is calculated for in the panel. So for all the moment values that we have in the panel, we'll go ahead and calculate for their respective area of reinforcement required and their respective area of reinforcement that we are going to provide in its place. So then moving on to our next sheet. This is the sheet that shows the area of reinforcement required for each section. Now the area of reinforcement has all been rounded up to the nearest whole number. So then we have the area of reinforcement in the bold and the ones in the brackets representing the area of reinforcement was provided. So from this sheet we can see our area of reinforcement required and the area of reinforcement was provided. So now this brings us to the end of the design of our section or our section for moment. Now because we are doing a slab design and slabs do not usually undergo shear, we have the liberty of skipping the shear check. If we cast our minds back to the first unit that we went through, we said that if you have a slab with a thickness of less than 200 millimeters, then it can pass without shear reinforcement, in which case you need not check for shear in that section. So then instead of going ahead to do a shear check, we are skipping that because our slab is relatively thin enough such that it shouldn't shear. Now when an element is that thin or when an element is not that deep, it usually fails in bending before it fails in shear. So then if my slab is exceedingly loaded, it would first fail in bending before it even moves ahead to fail in shear. That is why we are designing for the moment, but then not designing for the shear, because by the time it gets to the point of shear failure, it already would have failed in bending. So with that one done, we now move on and start with our serviceability limits check. We now start with our serviceability limits checks, and the first one that we'll look at is our check for the deflection. The first one that we'll look at is our check for deflection. Now, the first thing that we'll do is to calculate the actual deflection that occurred or that is likely to occur in our beam. So we have our actual deflection. And that one is calculated that one is determined using our span to depth ratio. So it's equal to our span divided by our effective depth. This is going to be equal to our span was 4,350 divided by the effective depth, which is 119. Dividing it by the effective depth, it gives us a span to depth value of 36.55. It gives us a span to depth value of 36.55. But then going through our BS code, it gave us span to depth limits, right? And from the beginning, the span to depth limits that we worked out with, which now becomes our allowable deflection. Which becomes our allowable deflection is 26. And now because we've introduced reinforcement into our concrete section, we'll now move ahead and modify the section, or we'll now move ahead and apply our modification factor. And from our previous unit, we said our modification factor was equal to 0.55 plus 477 minus Fs divided by 120, 0.9 plus m over d squared, and it should be less than or equal to 2.0. So then we'll now move ahead and determine the amount of modification that we can apply to our deflection limit by virtue of the amount of reinforcement that we've now put in our section. The Fs in our equation is giving us 2As required Fy divided by 3As provided. Then from our calculation, it's going to be 2 multiplied by our Fy is 250. Our As required, as we calculated, it was 274.12. Everything divided by 3 multiplied by our As provided was 377. This gives us an Fs value of 135.2. This gives us an Fy value of 135.51. 135.51. Then in terms of our m over bd squared, our moment at that section was 7.36 times 10 6 all over b is 1000 multiplied by a d, which is 119 squared, and this gives us a value of 0.519. So then our modification factor now becomes mf being equal to 0.55 plus 477 minus 135.51 divided by 120 into bracket 0.9 plus 0.519, which gives us a total modification factor of 2.55. But then our ms value 2.55 is greater than the 2.0 stipulated by the BS code. Our 2.55 is greater than the 2.0 stipulated by the BS code, in which case would let go of the value we've calculated and make use of the modification factor as given by the BS code. Since the BS code states that anytime you have a modification value which goes beyond 2.0, you let go of the modification value you calculated for and make use rather of the modification value provided in the code, which is the 2.00. With that one being said, we can now go and calculate for our allowable deflection. So then our allowable deflection is equal to 26 multiplied by the modification factor, which is 2, which gives us an allowable deflection value of 56. But then also, when we calculated for our actual deflection, we had an actual deflection value of 36.55, meaning that our actual deflection is less than the allowable our allowable deflection, in which case we can say that our our slab is compliant to the provisions of the BS code, and so our slab is our slab is good when it comes to the deflection check. So then with this one, our deflection check is, we can go ahead and say that our deflection is okay. We can now move ahead and say our deflection is okay. Now, having resolved for that, we now move on and do our second. Now, our second check has to do with the amount of cracks that would occur in the section. And when it comes to the crack check, the BS code has given certain guidelines that would help curtail the amount of cracks that would occur in our section. And this is based on how our reinforcements are distributed within the tension zone. An extract of that is provided for our viewing, and it states, in no case shall the clear span between bars exceed the lesser of 3 times the effective depth, or 75 millimeters. That is the first provision given by the BS code. It says, in no case shall the clear span between bars exceed the lesser of 3 times the effective span, 3 times the effective depth, or 75 mm, whichever be the lesser. If we take our reinforcement, we provided a reinforcement area, our AS provided was equal to 377 millimeters squared, and that translated into providing that translated into providing 12 mm diameter bars at 300 mm center to center. Now, what does this mean? It means that if I take my concrete section, my reinforcements are distributed within centers of 300 mm. So from the center of one reinforcement to the center of the other reinforcement, the distance is equal to 300 millimeters. But then the code is stipulating that the clear spacing or the clear distance between the bars, meaning that I'm supposed to come and estimate for the distances from the face of one reinforcement to the face of the other reinforcement. That will give me my clear spacing. Now, having in mind that my reinforcements are 12 mm in diameter, and the fact that my distances or my centers are starting from the center of one bar to the center of the other bar, for me to arrive at my clear spacing, all I need to do is to pick the spacing given by the spacing of my reinforcement and less out the diameter of my reinforcement bars. That will give me my clear spacing. My clear spacing equals to the spacing of the reinforcement minus the diameter of my reinforcement bar. So I less out the shaded regions from the total spacing. Now, once I'm able to subtract this from my total spacing, it will give me the spacing or the clear spacing between my reinforcement bars. Now, knowing that my reinforcement is being spaced at a distance of 300 and my reinforcement has a diameter of 12 mm, it tells me that my clear spacing between the reinforcements would have a value of 288 millimeters. I have a clear spacing of 288 millimeters, and per the provisions of the code, this value should not exceed 3 times my D effective. And given that my D effective is equal to 119 multiplied by 3. 119 multiplied by 3. It stands to reason that my clear spacing, which is 288, would fall below the 119 multiplied by 3. In which case I can go ahead and say that my my slab that I designed for is adequate against crack. So that my slab is adequate therefore is adequate against crack per the provisions that has been given. Now it further goes on to say that in addition, unless crack width are checked by direct calculation, the following rules would ensure adequate control of cracks for slab subject to normal internal and external environment. A, it says that no further check is required on bar spacing if either 1, grade 250 steel is used and the slab depth does not exceed 250 millimeters. No further check is required on bar spacing if either 1, grade 250 steel reinforcement is used and the slab depth does not exceed 250 millimeters. Now if we look at the slab that we are designing for, our slab depth or our total slab depth is equal to 150 millimeters, meaning that once my slab depth does not exceed 150 millimeters and I'm making use of mild steel bars, it means I don't require any other check for cracking. So then I can stop my check for crack at this level. Once I've satisfied this rule, it means that my slab is adequate against crack. So then my crack check is also complete. So then in a way, I'm almost done with my design. In a way, I'm done with my design of my reinforced concrete section. But then, in actuality, the calculations that we've gone through doesn't ensure that our design is adequate. Whatever calculation we've gone through we should be able to translate it from the numerical values as we have it into graphical values or into graphical terms. It is the graphics that will be taken to the site for the construction. So then, having come out with such nice values and having come out with a slab that has passed or that passed most of the checks that we've gone through, we should be able to convert whatever we've done into graphical terms. So then, based on the moment values that we designed for, we should be able to come and provide our reinforcement in the sections as adequate. So then, taking this as a sketch of the panels we designed for, we now go back to the area of reinforcement that we calculated earlier on, and we come and provide the reinforcement in graphical terms. So then, if we take our reinforcement, we had reinforcement for the tension zone. So then we come and provide our reinforcement for our tension zone, or reinforcement that are supposed to come and carry our tensile stresses. I'm just using a critical panel to illustrate. So that this might be my reinforcement within my tension zone. It goes this way and then it comes up. Now it's supposed to span from Then also I'll have another set of reinforcements which goes this way. All of these at the bottom of now. So after placing the reinforcement, you now come and adequately label the reinforcement. Now I can label this bar as R12. The R represents for the type of reinforcement we are dealing with, where R means mild steel, and T is for high tensile steel. For high tensile steel. So R12, and because I'm taking this one as my first reinforcement, I give it a bar mark of 1. So R12 1 at 300 centers or 300 mm center to center. Usually the reinforcement that is spanned along the short span, or the reinforcement that goes along the short span, are the ones that goes to the bottom of the section. So that if I'm supposed to take a section through, the reinforcement that goes to the bottom, or my R1201, is the reinforcement that would be at the bottom. So then because I have that one at the bottom, I label that one as B1. Then on top of that reinforcement, I have another set of reinforcements. So I come and call this one R1202 at 300 center to center. Because this set of reinforcement is lying on top of this reinforcement, I name it as B2. So all the reinforcement that goes to the bottom is being referred to as what? B1. All the ones that are lying on top of the bottom bars are being referred to as B2. So I have my B1 in blue, and my B2 are the ones that will come and lie on top of the B1 and are being shown as red. So then these are the reinforcements that will occur at the mid-spans. Now having shown my mid-span reinforcement, I now come and place my continuous, the reinforcement that would occur, or that would have to be at my support sides. So these ones would also come, depending on the type of support that they are on. So then I have this one also spanning from so this becomes my R1203 at probably also 300 center to center. And this, because it's occurring within my slab section, because that one is occurring at the support point. Within my support point, my tension zone would be at the upper part of the beam. So my hugging reinforcement will come this way with its distribution bars provided at the bottom. Now, because that one is occurring at the topmost part of the beam, it is usually referred to as top bars. And since that one is going to be the topmost bar, that one is being referred to as T1. Because that one is occurring at the topmost part of my beam, that one is being referred to as what? As T1. Then, having placed those ones, then the distribution bars for that kind of, or for that reinforcement, its distribution bars would also come. And the distribution bars would be placed only along the length of so that one also becomes R1204 at 300 center to center. And because that one is below the topmost bar, that becomes T2. So then you continue it this way, providing the mid-span reinforcement and the hogging reinforcement together with their distribution bars for all the moments that was calculated for, or for all the area of reinforcement that was calculated for. Now, once that has been done, at the end of the day, the final design or the final thing that would go to the site would look something somewhat like this, where all the reinforcements are being provided and a schedule for the reinforcement is provided on the site with section through the panel that has been designed. So ultimately, this is what we are aiming at, and this is what will go to the site for construction. Now, if you go through an accurate calculation and you do an accurate job with your analysis, but then translating it from the analytical stage to the graphical stage, we have H's there, then it means that everything you have done is cos 90. For you to get the best out of your design, you should be able to translate it from the analytical form into a graphical form, which should be interpretable, or should be able to be interpreted during the design or during the construction stage. That is why whilst we're going through the unit 1, at a point in time we said that to ensure durability of our structural element, the detailing of the structural element should comply with the element being designed for. So if you are designing for the slab, the detailing should go with the slab that we are designing for. You cannot go and import the detailings of one slab and come and superimpose on another slab. Whatever details you give to your slab should be one that agrees with the slab that you are designing for, and it should have been adequately or accurately transferred from the analytical stage onto the graphical stage, which would be used and would be read on the site. So at this point, we bring the design of our slab to an end. Thank you very much, and we'll continue from here by looking at the design of the staircase. Thank you.